Okay, welcome everyone to this continuation of quantum topology. Today I'm actually going to explain where the name comes from. Not really, it's mostly where I think the name comes from, but, well, we'll see. So, right now we are talking about braided categories, and I give you a second motivation for braidings. And this motivation is more, the other one was topological in nature, this is more like algebra in nature. So, quantum topology, sometimes called quantum algebra, is like a mixture between topology and algebra. So I give you two reasons to study braidings. We already had the one with knot theory last time, so braids knot theory, and today I try to motivate it as follows. So braiding is commutativity. So monoidal category. So people won't tell you, but a monoidal category is actually just an algebra with fancy pens. Right now, I don't have an addition. Later, we'll have an addition. So, strictly speaking, it's probably a monoid with fancy pens. But let's not care. Let's not worry about the difference here. So, monoidal categories usually are like algebras, but you have the extra structure of morphisms. That for many things doesn't do that much because morphisms are difficult to study. So people try to avoid looking at morphisms as long as you can. And if you really just ignore morphisms, then the monoidal category is nothing else than an algebra. Yeah? The monoidal product plays the role of the multiplication, right? You can multiply objects, and later you can also add objects. Right now we can't. So right now we can only multiply objects. But if you really follow this strategy of trying to avoid talking about morphisms too much, try to avoid as long as possible, it's difficult. Everything on objects is much easier. So maybe then it is a good idea to kind of mimic things you know about algebras or numbers, if you want, in category language. Yeah. And what could algebras be? Well, algebras are essentially matrices wearing fancy pens, if you want. So algebras are usually not commutative because they are matrices. So commutativity is a rare property in some sense of algebras, and maybe there should be some analog of commutativity in the world of categories. And that's exactly what the braiding is supposed to do. And I make this very precise on the next slide, but here enjoy my whatever picture of fancy pens. Excellent. So commutativity really just means xy equals yx, right? In category language, it's usually not a good idea to write equal, so you rather write they are isomorphic. Yeah? So x tensor y is isomorphic to y tensor x. You can commute them along you literally can commute them. You want to do a bit better because you're doing category theory. So instead of saying they are isomorphic, you say there is a specific isomorphism when we call it the braiding, satisfy some conditions. For example, we want it to be natural, which literally just means whenever you have a little coupon here, you can just slide it along the crossing. And I usually draw the beta as a crossing. So you can swap the places. It's a commutativity thing. But it's a specific choice of how to swap. And in principle, and also in many examples, you can have different choices how to swap. Yeah? So it's not unique, it's a choice. And this extra choice gives you something more. So, right? We are in category theory. We don't like equality. We like isomorphism. And, well, isomorphism means there's an extra choice, so we just make an extra choice and call that a braiding up to some axioms that we will see in a second, right? So braiding is a choice of commutativity. And this is this extra step, right? So here, literally, I always say it's an algebra, but it's an algebra with morphisms. So the morphisms are extra. And this kind of adds this extra information by choosing a specific isomorphism. And that's what category usually does. Just choose a specific isomorphism. It's usually better than just to say it's isomorphic. And it's like a standard thing in math, right? If you have a bijection between sets, if you just know set A is the same as set B from the size, that's okay. But usually it's better to have an explicit bijection. Maybe you're matching certain things and you just don't want to. Well, it's good to know that they're the same number of A's as the number of B's, but it's even better to know that there is a natural matching between them. And that's exactly the idea we do here. So the braiding is an additional choice of how to commute elements, if you want, objects in your I should have put elements in quotation marks, not objects. But anyway, how to commute elements in your monoidal category. And essentially the axioms we need, if you think about it for a little bit, yeah, sure, you want naturality. That's that thing. You can push a coupon up and down. Yeah, it makes sense. We want that. That looks very nice. And the only other thing you actually need, that's not quite clear that it's the only other thing you need, but turns out it is, essentially, is that there are essentially two ways to move x. So I'm using my little mouse here. There are two ways to move x past, I can zoom in. There are two ways to move x past yz. Either you do it in 2 steps, or you consider yz as one object and you do it in 1 step. Right? There's 2 ways to permute x across y and z, and they should be equal. That's essentially the condition, and you just do that for all possible combinations that you need, right? So there's also a version from the other side, like at the top here. And we'll see in a second that actually is a hexagon. It doesn't look like a hexagon, but it is a hexagon, and the corresponding axiom is called the hexagon condition. We'll see that momentarily. Not quite, because I wanted to explain where the name quantum comes from, quantum topology comes from. And it's really this idea of that the braiding could be now a choice of a non-trivial swap map, right? So overcrossing in a diagram is not the same as, so if this crosses under or this crosses over, it's not the same. Yeah? The swap map wouldn't see that. So and the case where these are equal, we call that symmetric. That's like the swap map. And this is usually like the usual commutative algebras. And then the big observation was that there's a whole zoo of somehow non-commutative algebras, if you want, that are still somewhat commutative. And this is where the braiding enters the game, where non-trivial braidings enter the game. And this is usually what people call quantum. So in this setting, it's called usually what people call quantum. It's meant in the sense of non-commuting. Yeah. So these 2 things are not the same. Yeah. These 2 things are not the same, and because we would be looking for categories where we find a non-trivial braiding. If you just think about vector spaces, then you have a braiding which just swaps vectors, but that's symmetric, right? That's a bit boring. You want to look for something more exciting, and people in the 1980s found many examples. Examples were known before, but in the 1980s they essentially found a machinery that creates exciting examples where you have a non-trivial swap, so an honest braiding, not a symmetric braiding, and usually that comes from something like quantum groups. Yeah? And this is roughly where the name comes from. Yeah? Quantum topology is the topology that you can get from quantum groups. Eventually, I probably will explain what quantum groups are. For now, you only need to know that there's some non-commutativity of these things involved. And this is where the name comes from. Quantum topology, doing topology with quantum groups. Essentially, that's what it is. I'm not 100% sure whether that's the real story, but that's how I experience it. And then the definition really looks like this. So here are 2 ways to commute x. Which one is not one I want to look at? The bottom one. Here are 2 ways to commute x to the end past y and z. So here's x in the front, here's x in the end. And the 2 ways to do it are like here, and it's now a hexagon. So you do it once. Yeah, so you just commute x along y and z, or you do it in 2 steps here and here, and it will be a hexagon instead of a triangle because there are some funny associators floating along, because they're always associators flowing along. You can ignore them if you want, and if you ignore them, then it's exactly just that picture. Yeah, the bottom is the bottom and the top is the top, if I haven't messed up, obviously. And then the braided category is actually really easy to define. It's just the natural choice of isomorphisms. Yeah, natural again is our little I can zoom up, I will scroll up, is this swapping condition. So a choice of crossing plus it satisfies the swapping condition, and it satisfies this type of move. I don't even know how to call it. Hexagon move. It satisfies the hexagon move. And that's surprisingly everything you need. And then it's mostly well, up to trying to find braidings on a category. Anyway, I hope you enjoyed this video, and I also hope to see you next time.